Lighthouse Scientific Education presents a lecture in the Measurement in Number series. The topic is Dimensional Analysis, Part 1 and Part 2. Material in this lecture relies on an understanding of the previous lectures, Math for Chemistry, Scientific Notation, and the Metric System. Dimensional Analysis. This lecture has one topic in two parts. The first part is for all students. The second part are for those students that are expected to use dimensional analysis for multiple part equations. If you suddenly discover that you are supposed to be one of those second part students, and you've only watched and practiced the first part, well, reopen the lecture and watch the second part. In the first part, we will begin with a unit definition. Then, to the introduction of conversion factors, followed by a discussion of conversion factors focusing on following units. We will add perspective with examples of converting units. In the second part, we will expand on the concepts of conversion factors, looking at multiple step conversions. First, we will perform the calculations one step at a time, then just using one long equation. And finally, we will look at multiple unit equations. Before we start on conversion factors, it would be helpful to clear up the meaning of the term unit. The term unit is widely used in chemistry, and following units can be very helpful in understanding how to solve problems and catch mistakes. There are two uses of the term that we should cover. 1. Unit means one. A unicycle has one wheel. A unicorn has one horn. In math, a unit circle has a radius of 1. In chemistry, a unit factor, a subject we will cover in depth soon, is a fraction that has the same value in the numerator as the denominator and is therefore equal to 1. 10 in the numerator over 10 in the denominator is 1. 10 divided by 10 is 1. The second use, unit, refers to the type and denomination of a measurement. That is the kind, type, and size of a measured or given value. In 12 inches, the inches are called the units. The type is length, and the denomination or quantity size of the measurement is inches. 12 inches is really 12 times 1 inch, 12 inches. In 3 liters, the liter is called the unit. 3 liters is really 3 times 1 liter. So when the term unit comes up in your study of chemistry, it is probably referring to the type and denomination of a measurement. Dimensional analysis is a mathematical method for comparing the units or dimensions of a physical quantity, such as a measurement. The comparison or conversion from one unit or dimension to another is generally accomplished by a conversion factor. Conversion factors are a tool for changing units of one measured or given values into different units without changing the value. The measured or given value just means a number with units that are attained in the lab or found in a homework problem. The new units will be of the same kind of measurement. That is, if the original units were length, then the converted units will also be length. A simple example would be feet multiplied by a conversion factor to give an equivalent amount of inches. Different units, same unit type. Another example would be changing speed, miles per hour, into an equivalent or equal amount of miles per minute using a conversion factor. Conversion factors, or CFs, are about the canceling of units. And this will occur when a term in the numerator is the same as a term in the denominator, just like simplifying fractions. A feet unit will cancel out if there's a feet unit in the top and the bottom of a fraction. Feet over feet cancel. An hour unit will cancel if there is an hour unit in the top of the fraction and in the bottom. Hour over hour is 1. They cancel. The development and application of conversion factors can prove initially confusing. We will, therefore, build a reason-based foundation that will give not only how to, but also a why. We generally find two different placements for units that are being converted. It's important that we recognize the difference to ensure that canceling of units occurs. Here we will just clarify what the placements are and begin to familiarize ourselves with the concept. The first placement is when the given or measured value has units to convert that are in the numerator. This will also include units that are not in a fraction. In this basic format, the numerator of the conversion factor has the new or the desired unit type, and the denominator has the old or current unit type. So that we are clear on the terminology of the fraction, new units are what the conversion will give us, and they are over old units, and those are units that we started with. This can also be said, the units we desire over current units. And we will use this phrasing frequently. Another comparable phrasing is the units we want over the units we have. They're all saying the same thing. Now we'll consider the second type of placement. The given or measured value has units to convert that are in the denominator of a fraction. In this mile per hour example, the hour units is in the denominator, and they are said to be converted into minutes, which are also in the denominator. For such units, the numerator of the conversion factor has the old or current units, and the denominator has the new or desired units. These conversion factors are the reciprocals or the flip of the conversion factors that convert units that are in the numerator. Now, don't be too concerned that you have to memorize the order of the fraction. The construction of the fraction will become clearer as we continue the development of the basic concepts. And that leads us to our next concept, following units in conversion factors. We shall now see why the orientation of the current units and the desired units are the way they are in conversion factors. Again, it is all about canceling out the current units. The process of converting units is a mathematical one. The given or measured value has what we call the current units. It is multiplied by the conversion factor, yielding a value in the desired units, the units we want. Let's look just at the units and see how the math works. For demonstration purposes, we will turn the current units into a fraction. Anything can be made into a fraction by dividing by 1. Doing the fraction multiplication, numerator times numerator over denominator times denominator, we have current units times desired units over 1 times current units, which is just current units. We see that both the numerator and denominator have the term current unit, so they can be crossed out or canceled out, leaving just desired unit. Quick question. What would happen if we did the same thing, except that we had the conversion factor upside down, current on top, desired on the bottom? This does not produce the desired units. Doing the fraction multiplication, we have current units times current units over 1 times desired units. There is no canceling, and we do not end up with our desired units. It's not that the desired units over current units is just wrong. It is that the current units did not cancel out. However, if the measurement of interest has units in the denominator, this conversion factor will work. Time is often a unit in the denominator. For a long time, movies were shown at a rate of 24 frames per second. Second is a unit in the denominator. A look at the math will show us the proper canceling of current units in this circumstance. Multiplying numerators gives us 1 times current units, and multiplying denominators yields current units times desired units. Current units cancel out, and the conversion is complete. So the objective of a conversion factor is to cancel out current units and leave desired units. If the current unit of the given value is in the numerator, then the conversion will have the current unit in the denominator. But if the current unit is in the denominator of the given value, then the conversion factor will have it in the numerator. These exercises highlight one of the most important tools in problem solving, canceling out units and verifying that you end up with the type of units you want. This prevents mistakes. Make canceling units a standard practice and you will be rewarded for it. To finish our construction and deployment of the conversion factor, we will need the unit factor. A unit factor is a fraction that has the same value in the numerator as the denominator and is therefore equal to 1. This should look familiar because in a conversion factor, the numerator has an equal value to the denominator. Conversion factors are unit factors. So a conversion factor in length might look like 12 inches over 1 foot. 12 inches equals 1 foot. Numerator equals denominator, and the conversion factor is therefore equal to 1. Not 1 foot or 1 inch, just 1. A conversion factor in time might look like 60 seconds over 1 minute. 60 seconds equals 1 minute. Numerator equals denominator. It has a value of 1. And a conversion factor in volume might look like 1,000 milliliters over 1 liter. 1,000 mils equals 1 liter. Numerator equals denominator. And you guessed it, the fraction is equal to 1. We can construct a unit factor or a conversion factor from any equation relating to units of the same measurement type. That means we can always make our own conversion. Here are 3 simple steps. Begin with an equality. And you will want to select an equality that relates the current units of the given value to the desired units of the conversion you want. For something like foot and inch, the numerical relationship is well known. Other relationships may require you to look up that equality. The next is to divide both sides by one of the sides. We will try to divide both sides by 1 foot. The last step is to solve. 1 foot divided by 1 foot is equal to 1. Anything divided by itself is just 1, no units. Now we see that the conversion factor of inches over 1 foot is really just a fancy way of saying 1. What if, instead of dividing by 1 foot, we divide each side by 12 inches? This will create a situation where 12 inches over 12 inches is equal to 1. And we have a new conversion factor that is the flip or reciprocal of the first one we created. And since it is also equal to 1, it is equal to that reciprocal. They're both fancy versions of the number 1. We are now ready to knock out some conversion examples. Problem 1. We have 22.2 feet, and we want this given value in inches. The conversion factor that we need has to have the current unit, feet or foot, in the denominator, and the newer desired unit, inches, in the numerator. That's 12 inches over 1 foot. The numerator is equal to the denominator, a conversion factor. Our orientation of the conversion factor is correct because the units of feet cancel out. There are several ways that we can write this mathematical expression. The multiplication sign here works just fine, but we will use parentheses. The multiplication sign is no longer needed since it is implied that the value in front of the parentheses is multiplied by the value inside. Returning to the problem, doing the math, 22.2 times 12.0 divided by 1 is 266 inches, to 3 significant figures. There is only one way for this equation to be true. That is if 12 inches over 1 foot was equal to 1. According to the identity law of multiplication, multiply a value by 1 returns the same value. So the ratio of 12 inches over 1 foot must equal 1. Not 1 foot, not 1 inch, just 1, no units. Our next problem, we have 24 frames per second. Yay, movie speed. And we want to convert into frames per minute. The conversion factor has seconds on top and minutes on the bottom. 60 seconds equals 1 minute. 60 seconds over 1 minute equals 1. We cancel out seconds, leaving minutes, and doing the math gives us 1,440 frames per minute. Our last example starts with 0.441 liters, and we want to convert into milliliters or mils. Our conversion factor should therefore have mils on top and liters on the bottom. Well, how many mils are there in a liter? This is a good one to memorize if you don't know. It's 1,000. 1,000 mils per 1 liter. We cancel out our liter units, leaving just mils. Do the math, and we have 441 mils to 3 significant figures. This last example shows how much easier it is converting in the metric system, since the answer has the same numbers, 441, but the decimal point is in a different place. With all the basic steps of conversion factors in place, and a few examples under our belt, we can test our detailed understanding of the process with some practice problems. We start with having the measured value of 1.1 pounds, and we want to convert that into ounces. Step 1 of developing a unit factor as a conversion factor has us finding an equality that relates to units, pounds, and ounces. If you know that, great. If you don't, look it up. Happens to be 1 pound equals 16 ounces. The next step is to divide both sides of the equality by one of the sides. But which one? Should we divide by 1.0 pounds and generate this unit factor? Or by 16 ounces and generate this unit factor? What we want is for pounds to be in the denominator so that the units will cancel out. And we verify our choice by actually canceling out pounds in the numerator and pounds in the denominator, leaving just ounces. Now we do the math. 1.1 times 16 and come up with 18 ounces to 2 significant figures. Let's try another. Given 67.0 centimeters, find an equivalent amount in meters. Note that the centimeter we have has 3 significant figures, with the 0 being significant, as it was included with the other numbers. Again, we start with an equality that relates units that we have, our current units, centimeters, with units that we want or desire, and that's meters. From our study of the metric system, we know that 1.00 meters equals 100 centimeters. The 1.00 is actually an exact value, like 100. So we can just write it as 1 meter, which has an infinite number of significant figures. Now we have to decide whether to divide both sides by 100 centimeters and generate this unit factor, or by 1 meter and generate this unit factor. Our decision is based on canceling units. We want centimeters in the denominator. 1 meter over 100 centimeters. Verify our choice by canceling out centimeters, leaving just meters. Dividing 67.0 by 100 gives us 0.670 meters to 3 significant figures. This is the end of part 1. The conversion shown here will generally be sufficient for the early part of chemistry and can be mastered with a bit of practice. In part 2 of this lecture, we will use the same steps as outlined in part 1, but we will use them multiple times in each problem. These too can be mastered with an understanding of the basic principles and a bit of practice. Some conversions require multiple unit factors. A conversion of multiple units or multiple unit factors can be done one step at a time. Later we will solve similar problems in a single equation. A good practice is to first think through the method of conversion in a stepwise manner. Consider this conversion. How many seconds are there in 3.31 years? Current units, years, desired units, second. Not many people know an equality that relates seconds to years, but most people can get there using one or more set of equalities. All this means is that we're going to need multiple unit factors, and the basic steps are already described. For multiple unit factors, convert the current units to a new unit that is closer to the desired unit. Repeat until solved. Before we start with the math, we can lay out a path of known equalities that link together the unit years to the unit seconds. We begin by asking, is there an equality that relates years to a unit that is smaller than years but larger than seconds? How about days? There are approximately 365.25 days in a year. Later we will generate a unit factor from this and convert years to days. Staying with generating a path, we ask the same type of question. Is there an equality that relates days to a unit that is smaller than days but larger than seconds? And the answer is yes. We know that 1 day equals 24 hours. Later we will generate a unit factor from this equation and convert days into hours. Continuing on, is there an equality that relates hours to a unit that is smaller than hours but larger than seconds? Obviously. Minutes will do that. And we are ready to convert into seconds. The last link is in place. We now know the path from years to seconds, and if we do each step of the path separately, we can combine them into an overall conversion. We begin by focusing on the first step of the path. We can reword this main question not to ask for seconds, but to ask for days. How many days are there in 3.31 years? Well, do we know an equality that relates years to days? Yes. We stated the equality 1 year equals 365.25 days. Since years are our current unit and will only cancel out if there are years in the denominator, our unit factor is days over years. Inserting the unit factor as the conversion factor, canceling out years leaves just days. We get out our calculator and multiply 3.31 times 365.25, and we get 1,209 days. Since we're going to use this value in the next calculation, we do not need to worry about significant figures. That will come after the last calculation. We can take that days value and use it in the next conversion, days to hours. The question now becomes, how many hours are there in 1,209 days? And since 1,209 days equals 3.31 years, we're actually asking the same length of time. Days is now our current unit, hours our desired unit. The equality 1 day equals 24 hours leads us to the unit factor of hours over days, which has days in the denominator that will cancel out with current units, leaving just hours. Multiplying 1,209 times 24 yields 29,016 hours. Quite a long time. Keeping that 29,016, the process moves on to the conversion from hours to minutes, and the question becomes, how many minutes are there in 29,016 hours? Hours is now our current unit, minute is our desired unit. Equality 1 hour over 60 minutes leads to the unit factor of minutes over hours. Inserting the unit factor and canceling out current units hours, leaving just minutes. Multiplying 29,016 times 60 gives us 1.7410 times 10 to the 6 minutes. Here scientific notation comes in handy. Our final conversion is minutes to seconds. The question becomes, how many seconds are there in 1.7410 times 10 to the 6 minutes? Minutes is now our current unit. Seconds is our desired unit. The equality 1 minute equals 60 seconds leads to the unit factor of seconds over minutes. Inserting the unit factor, canceling out minutes, leaving just seconds, and multiplying 1.740 times 10 to the 6 times 60 gives us our final value of 1.04 times 10 to the 8th seconds to three significant figures. And to recap, how many seconds are there in 3.31 years? In 3.31 years, there are 1,209 days. In 1,209 days, there are 29,016 hours. In 29,016 hours, there are 1.7410 times 10 to the 6 minutes. And in that many minutes, there are 1.04 times 10 to the 8 second. Therefore, 3.31 years are 1.04 times 10 to the 8th seconds. Multiple step conversions can be broken down into individual conversions, but they don't necessarily have to be separated. Conversion of multiple units or multiple unit factors can be done in a single equation. We can ask the same question, 3.31 years to seconds, to demonstrate the process. In effect, we ask the same series of questions and come up with the same series of links, but we stay with one equation. The first question is, how many days in 3.31 years? And so we use the same unit factor to answer it. Years cancel out, leaving just days. And if we were to do the math, right here, we would get the same answer, 1,209 days. But we're going to hold off on that right now. Next, we ask the days to hours question, coming up with the same unit factor. Day units cancel out, leaving just hours. And if we were to do the math right here, and we're not, we'd come up with the same answer, 29,016 hours. Proceeding on to minute conversion with the same unit factor. Hours cancel out, leaving minutes. Punching these numbers into our calculator at this point would give us 1.7410 times 10 to the 6 minutes. The final conversion is into seconds. Same conversion. Minute units cancel out, leaving the desired units of second. And now we do the calculation of this long equation and get the answer to the question of how many seconds there are in 3.31 years. 1.04 times 10 to the 8 seconds to three significant figures. Unit factors equal 1. The only way for 3.31 years to equal 1.04 times 10 to the 8 seconds in this equation is if 3.31 years is multiplied by 1 times 1 times 1 times 1. Unit factors at work. While we have the equation up, let's discuss how to enter it correctly into your calculator. Begin by multiplying all the numerators together. 3.31 times 365.25 times 24 times 60 times 60. Divide by each denominator. Divide by 1, by 1, by 1, and then hit equals. In practice, there's no need to multiply or divide by 1. Just skip the ones. And just to cover all bases, some chemistry textbooks use a grid instead of parentheses to keep track of the numbers. It can be thought of connecting all the fractions into a chain. Each step and every thought, however, is exactly the same. Begin by putting 3.31 years in the numerator spot of the front box. Remember, each number can be made into a fraction by dividing by 1. In practice, you can skip putting a 1 here. And now begin to make conversions. Each new column is a unit factor. The first column is years to days. Cancel units. The next column is days to hours. Cancel units. Minutes to hours, cancel units. And finally, minutes to seconds, cancel units, leaving just seconds as the final unit. Multiply the numerators, then divide by the denominators. Both parentheses and the grid are acceptable ways of doing the conversion. They are the same thing. It is a matter of preference and perhaps what your instructor likes. Another example is in order. We will do it one step at a time, then combine each step by inserting the unit factors and canceling the current units. The question is, how many meters are there in 4.28 feet? 4.28 feet is the current units. Meters are the desired units. For convenience, the equality of 1 inch to 2.54 centimeters is provided. It is the only exact conversion from U.S. standard units into metric system. The significant figures are therefore infinite. Our strategy is to convert the units to a new unit that is closer to the desired unit and repeat until solved. As with the previous problem, we should work out the steps in our conversion before generating unit factors and doing math. We are starting with feet, and we want to get to meters. There is going to be a conversion from U.S. standard to metric. Keep the inch to centimeter conversion in mind as we proceed. From feet, a new unit closer to the desired unit might be inches, since inches to centimeters is a known conversion. 1 foot is equal to 12 inches. From inches, we can use the conversion to get centimeters. Now that we're in the metric system, we can use our understanding of prefixes to get the equality 100 centimeters equals 1 meter. Again, it's an exact relationship with infinite number of significant figures. We have all the parts to address our conversion. We begin as in the previous problem and change the question to answer one-step conversions. How many inches are there in 4.28 feet? We have the equality, and if we divide by feet, we have a unit factor with feet in the denominator. Plugging it in and canceling feet, leaving inches, and doing the math gives us 51.36 inches. Again, we'll worry about significant figures after the last calculation. We will keep that 51.36 inches and move on to our next conversion, which is inches to centimeter. We can rewrite the question to ask how many centimeters are there in 51.36 inches. Here we use the equality provided. Since we want to cancel out inches, we need to divide both sides by 1 inch, yielding the following unit factor, which we insert as a conversion factor and cancel out the current units, leaving the desired units, centimeters. Doing the math leaves 130.45 centimeters. On to our final conversion. Centimeters to meters. Our last rewrite, how many meters are there in 130.45 centimeters? We employ the equality 100 centimeters is equal to 1 meter. We produce the unit factor 1 meter over 100 centimeters. Plugging it in and canceling out centimeters leaves just the desired units of meters. And asking our calculator for a little help gets us 1.30 to 3 significant figures. And that's driven by the 3 significant figures of the starting value 4.28. As we did in the first multiple unit factor example, we will keep the starting problem and solve it using just one equation by combining the individual conversions. We use the same stepwise logic in going from feet to meters. The first conversion is from feet into inches. We use the same equality and the same unit factor. Foot units cancel, leaving inches. If we were to do the math, and we're not, it would be 51.36 inches. The next conversion is inches to centimeters. Canceling inches units, leaving centimeters. If we were to stop here and punch the numbers into our calculator, we would get 130.45 centimeters. The final conversion is centimeters to meters. Input 1 meter over 100 centimeters. Cancel centimeter units out, leaving meters. Now we do the math. 4.28 times 12 times 2.54 and get the conversion 1.30 meters. Remember, we skip multiplying dividing by 1. As we see, both ways yield the same value. This one takes a little more practice to get the hang of. Though the nice thing about the single equation is that you can more easily double check your units to make sure that you haven't flipped a unit factor upside down. Because these lectures will predominantly use parentheses over the grids as a means to solve chemistry problems, we will cover the grid one more time for those who will be using it regularly. Start with the grid. Insert the current units. Using the same logic, enter the first unit factor, feet to inches. Cancel units. Next unit factor, inches to centimeters. Cancel units. And then finally centimeters to meters. Cancel units, leaving the desired units, meters. Do the math. To round out our discussion on unit factors, we will do a problem that has multiple units, including current units, in the denominator. We do it as a single equation. The question is, an air molecule is moving 501 miles per hour. How fast is it going in kilometers per minute? The current units are miles over hour. That's distance over time. We want to get kilometers over minutes, also distance over time. Our approach will be the same as the other multiple step conversions. We will reason out a stepwise conversion. For each step, generate a unit factor from an appropriate equality. A good rule of thumb for multiple unit conversions is to consider just one unit conversion at a time. That limits confusion. We will begin by considering the conversion of length units from miles to kilometer. We can employ the same path between standard US units and metric units that uses that 1 inch equals 2.54 centimeters. Or we can look up an equality directly between miles and kilometers. That is easier and shorter. That equality can be found relatively easy. It is 1.00 miles equals 1.61 kilometers. This is not exact, so we will need to count significant figures. And there is 3 in each. The conversion will get us into units of kilometers over hours. The distance unit is complete. On to the time unit in the denominator. Do we know a conversion from hours to minutes? Yes, we do. This conversion will give us the desired units of kilometers per minute. So we have our stepwise logic and the equalities to generate the unit factors. We're ready to knock this conversion out. We will begin with the numerator, the miles to kilometers. Using this equality and recognizing that miles, the current unit, needs to be in the denominator of the unit factor to cancel out, we generate the unit factor 1.61 kilometers over 1 mile. The units do cancel, and they leave kilometers over hours. Now on to the denominator. The equality is a familiar one, but unlike the previous unit factor, the current units will need to be in the numerator to cancel out. Therefore, the correct unit factor has 1 hour over 60 minutes. And yes, hours do cancel out. What is left over is kilometer in the numerator and minute in the denominator. Doing the math yields 96.6 kilometers per minute to 3 significant figures. Conversion and unit factors are necessary tools to do chemistry. Establish a procedure, like how we did them here, and do it that way every time. To recap, dimensional analysis is a mathematical method for comparing the units or dimensions of physical quantities. Conversion factors are tools for changing units of measured or given values into different units, though of the same type. Conversion factors are about canceling. Old or current units cancel out, leaving the desired units. The arrangement of old or current units to new or desired units depends on where the units are in the given value. If the given value has units to convert that are in the numerator, then these old or current units must be in the denominator to cancel out. If the given value has units to convert that are in the denominator, then these old or current units must be in the numerator to cancel out. Conversions, or multiple units or multiple unit factors, can be done one step at a time or in one step. And that concludes our lecture. Remember to practice what you've learned to truly build understanding. And really, this one takes some work.